Good day, everybody. So now let's take a look at our topics that will precede the second exam. So, and here, according to what you saw in the old exam, these are the topics that we are going to cover, right? But of course, they need to be adjusted a little bit to our actual course. So do not overly rely on the old exams. So they just are designed to sort of give you the understanding of what the questions looked like in the past. So that's kind of the emphasis here. So the questions might be similar to what we will have in the future, but by no means the old exams are completely identical. They could be identical to some extent to the new ones, but there is always some sort of difference, right? So that's just kind of a disclaimer. So that's why we're just going to take a look at some underlying concepts leading up to our second exam. So, and the first one, so like what we can start with is before we get to, let's say, the reactions, which was a relatively new topic for this kind of like set of themes between exam 1 and exam 2. So we're going to take a look at the carbon atom geometry, right? So previously we were talking about alkanes, right? That was our first family of organic compounds. Then we switched or continued our conversations about alkenes and alkynes, right? So then what was different there is the nature of the carbon atom. That's in those compounds. So if you take a look at that situation, you can think about like three possible geometries for the carbon atom, right? And hybridization. So those things kind of go hand in hand. So if we start with like alkanes, for example, then the bonding pattern is also specific to carbon atoms. In alkanes, it's going to be looking like that, right? So it is just 4 single bonds, and then the carbon atom is tetravalent. So if we think about the hybridization, so the hybridization type here is sp3, and geometry here is going to be tetrahedral, right? Or that's the adjective. The noun will be here tetrahedron, right? So the carbon atom looks like a tetrahedron, or it is tetrahedral. Tetrahedral. So that's just kind of like the fact of the matter that we need to keep in mind when we think about questions like, okay, well, what's so special about this carbon atom, right? So first of all, let's take a look at the bonding pattern, right? How can we identify or see the bonding pattern? Well, perhaps it's going to be a good idea to be able to switch from the skeletal drawings to expanded drawings, right, of various organic structures, which ultimately will lead you to kind of identification of the bonding pattern around the particular carbon. So this one is sp3, 4 single bonds, right? So I kind of emphasize that because it's peculiar to sp3 hybridized carbons specifically. So then geometry is tetrahedral. So that's our case 1, for example. Then moving on to case 2, that's something that we can see, for example, in alkenes, for example, right? So it's going to be this type of situation. We have the carbon, which is also tetravalent, but the bonding pattern or the bond arrangement grouping is a little bit different, right? So we'll still have single bonds, but it's going to be only 2 of them, right? So now the other 2 bonds are combined into the so-called one double bond, right? So that's one double bond right here, one single and another single. So we have total of 3 bonds. So the hybridization type here is sp2, and then geometry of this carbon is trigonal planar. So trigonal, so that word, oh, sorry, so trigonal. So trigonal, planar. So this word resembles the word triangle, basically. So if you look at this geometry, it looks like a 1, 2, 3, right? So 3 vertices of the triangle in this case. So trigonal planar geometry. So this is like not a 3D structure. It's kind of like plane, right? So you can put it in the plane of a sheet of paper, for example, this type of carbon, right? So whereas this one is a 3D carbon. So it is a tetrahedral shape, which you need to which you cannot just put on the plane table and then make them merge, right? So this is going to be a 3D shape. This is more like a 2D shape. So sp2, trigonal planar. So that's what we can see, for example, in alkenes, right? And then as you hear those terms, maybe it's going to be a good idea to kind of ask yourself some kind of Follow-up questions. What is an alkene, right? So what do we need to have in the compound to call it an alkene? Is it a triple bond? Is it kind of like a double bond? Or is it some kind of cycle with alternating double and single bonds, right? So I kind of like throw lots of deception in there, so which is kind of like designed to for you to highlight the path to the kind of like truth and true answer, right? So yeah, just kind of something to keep in mind. So trigonal planars. So let's finish this word. And then finally we were looking at alkynes, right? So which also have a peculiar bonding pattern which looks like this, right? So carbons in alkynes will have a triple bond, right? So as long as we have a carbon-carbon triple bonds, then we are going to have an alkyne, right? So here we go. So that's what the alkyne carbon geometry will look like. So basically we still have 4 bonds total, right? It is a tetravalent carbon. It's by no means like divalent, for example, right? Or something like that. So yeah, every bond, right? So speaking of definitions, right, from the past exam. So if you look at the covalent bonds, so for the covalent bond, what do we need to have, right? So make sure that you also kind of like keep your terms clear. So like when you think about the bonding between, let's say, carbon and H or carbon and carbon, it's a bonding between atoms. C and H or C and C are not molecules, right? So they are atoms, but the atoms will make the molecules, right? So if you think about, let's say, like CH4, right? Methane. So it is a molecule, right? It's combined of 1 carbon atom bound to 4 H atoms, right? So that will become a molecule. But if you think about the just like a covalent bond, it's not between molecules, it is between atoms originally, right? Maybe, yes, as a result of the reaction, so we will kind of bind molecules, right? Such as like ethylene and H2, for example, but it's like the further kind of like development in our skills. So, but for now, that's the bonds, right? So that we think about. So maybe you have some kind of like alkyne will be looking like this, right? It will have 3 bonds around or surrounding the carbon atom. So 3 bonds total. And then what happens is that we have the bonding pattern, which is going to be 1 single bond and 1 triple bond. So total of 4 bonds as well, right? To correspond to tetravalent carbon here. So the hybridization type is sp, and then geometry here is, so if you look at this drawing, right? So if you start drawing that correctly to begin with, so then you'll be able to identify the geometry. So it is just here, straight line, right? So we'll call it a linear geometry. So, and then this angle here will be like 180 degrees, right? Here, the angle, just like in the triangle, right? So this is like a triangular kind of like splitting here. So 360 split into 3 equal angles. So angle here between the bonds is 120 degrees. So here, the angle is kind of like shown in a little bit of like strange fashion because it's a 3D structure. So, but the angle between the single bonds in the sp3 hybridized carbon is supposed to be like 109.8 degrees or something. So that's kind of like 108, 120, and then here we have 180. And so that's how the angles progress. So linear, and that's it. Right, so then let's move on from those kind of like carbons to what? Let's think about the Lewis pairs, right? So because these are not the Lewis pairs, but the Lewis structures and lone pairs specifically. So this is something that we'll see a lot. So because, why? Because we are introducing slowly, as you can see, heteroatoms, right? So the atoms, which are kind of like fundamental to organic chemistry, are carbons, right? Carbon and hydrogens. So, and then as we can recall, so those atoms are sometimes, or they not always can be shown in the structure, especially if you use, for example, the skeletal structure of the compound, right? So it's going to be just kind of like lines and angles. That's what it's literally called, line angle structure. So, and then those like carbons and hydrogens atoms are implied. So now if we take a look at some other atoms that are called heteroatoms, which are not carbons and hydrogens, so those are typically oxygen, nitrogen, sulfur, right? So that's what we will be looking at down the line. So for those atoms, it's going to be a good idea to kind of like know their Lewis structural representations, right? So we didn't start looking at sulfur compounds yet, so let's just not overwhelm ourselves with that information. Let's take a look at oxygens and nitrogens, right? So previously we were looking at NH 3, for example. So this compound has a lone pair, one lone pair, right? So now that let's take a look at the water, right? So it's going to be having two lone pairs like this. So that's H2O. Why are we talking about that? So those compounds are like easier in structure, right? To be honest, compared with they are kind of like organic, I would say, build ups, right? So because if you think about it, so like many people mentioned in the past, so how do we kind of like theoretically go from like simpler molecule to a more complicated molecule, right? So if we just like don't care yet about like complicated synthesis, synthetic pathways and such reactions, right? So we can just say, okay, well, looks like for example, if we want to go from the NH3 to some sort of amine, right? So we have here CH3. So carbon is bound. So that's what you need to understand. So because there is no divalent H's or something like that, right? So carbon is singly bound. So it has like 3 single bonds to 3 H's, right? And then it has a single bond, carbon single bond to NH2. So basically here we have the amino group, right, emerging in front of ourselves. And then what you can see here is just one of the hydrogens here was removed, right? So the NH bond was broken, and then it was switched to the CN bond, right? So CN bond was made, and now we switched one of the hydrogens in the NH3 molecule to CH3, right? So now we have a more complicated structure, conceivably. So what happens is that, however, some things carry over, such as the lone pairs, right? Still stayed, right? So the NH bond was intact, but I mean, it was kind of like not intact, but it was engaged, right, into the new bond formation. But the double, like two electrons, a pair of electrons here is still intact, right? And then it carries over to your amine molecule, right? So it's pretty good, right? Just think about like what's kind of like affected, what's staying intact, right? So, and then if you know some kind of like simpler structures, you might as well kind of like try to use them as proxies to build more complicated structures and then carry over certain features, right, of those simpler structures into more complicated structures, such as the lone pairs, right? So same could be true about this water molecule, right? So let's imagine that we are going to break the OH bond. What's going to happen is that we'll have the leftover stuff, which is going to be just basically like leave that oxygen with the lone pairs alone, right? And then the OH bond, like number 1. OH bond number 2 is broken, right? So now we can have, for example, here CH3 again. Well, let's make it CH2, CH3, right? Let's make it a little bit more interesting. Like it's going to be like ethyl group here. So now we have the alcohol. We have this carbon-oxygen bond. In lieu of this kind of structure, like COH structure right here. So yeah, that's what we are going to have. And now we went from basically the water, right, by like breaking this OH bond and switching H to the carbon and or like ethyl rather, right, and then making the CO bond. We now arrived at the alcoholic structure. So this is going to be our ethanol, right, ethanol molecule. So then see here, so you have some kind of features circled here that carry over, right? So divalent oxygen, so two lone pairs. So like it's pretty good, right? So now let's take a look. So we are going to kind of like move on to alcohols. So since we started talking about loose structures, right, and OH bonds. So what we started kind of like doing about alcohols is that we were looking at the alcohol ionization, right? So apparently like alcohols contain this like OH bond here, right? So which is polar compared with CH or CC bonds, which are considered non-polar, right? So for the reasons we discussed in the past. So now maybe it's going to be a good idea to review, right? What are the reasons? Like why is CC or CH bond non-polar all of a sudden, right? But why is an OH bond polar, right? So that stems from the general chemistry prerequisite knowledge, to be honest. So, yeah, so that's what we have. So where was I? Okay, so but now the OH bond is polar, right? So the polar bonds are known for their ability to break more easily than non-polar bonds, right? So for example, it's not that easy to break CH bond, right? So that's why, for example, if you look at like alkenes specifically, so we know from the past that they are considered non-reactive. Why? Because in particular, it's not easy to break the CH bonds since it is non-polar. As you see, you can kind of scaffold your knowledge here. So non-polar, not so easy to break. Consequently, the entire compound, let's say like I don't know, hexane, right, becomes unreactive. And then there is a further ramification or further like scaffold stair, like in the staircase, right, of knowledge. So you can use alkanes, such as some alkenes, lots of alkenes, to be honest, such as like hexane, for example. You can use it as a solvent, right? So it is just going to be the solvent for various chemical processes because this is going to be like serving as a medium to carry out the chemical reaction. Other chemicals will react, but the hexane will stay intact and will be used as a solvent just to hold the chemical reaction, right, of sorts. And it could be used as such, right, because it is just unreactive, right? So that's what we need for the solvent. So it just doesn't have to like burn or decompose. It's going to be kind of like very bad, chaotic for the chemical reaction, right? We want the solvent to stay kind of like put, so to speak, right? So no bond deconstruction in the solvent. So yeah, anyway, so but OH bond is more reactive compared with CH bonds. So then what could happen is the so-called acidic behavior accompanied by the ionization, right? Again, you can see the scaffolding of the knowledge here. Ions, right? Acidic behavior. What's acidic behavior? That's the proton donation. So now let's show the proton donation in the case of some kind of like random alcohol, such as maybe this one, right? So let's do the like 1-butanol, for example, 1-butanol. So we can show that now as a skeletal structure. 1, 2, 3, 4. So you have your carbons. 1, 2, 3, 4. Okay. So then we're going to have this. So that's going to be our bond. Okay. So that's 4 carbons, 1 oxygen with its respective lone pairs. And then we have this like OH bond, which we can show explicitly, which will be ionized, right? So if we want to show the ionization, so alcohols are considered weak acids. So that's just kind of the empirical, experimentally derived knowledge. In other words, right? That's what like empirical stands for. So experimental. So you just kind of like do that and then see what happens. So then we're going to have dissociation here. So acidic behavior means that we must show the H plus generation. So we will have our kind of a carbon skeleton intact, right? So this just stays put. So then we're going to show this like bond here. It also survives. Carbon-oxygen bond still stays, right? So now the OH bond is broken. So let's kind of like break it, right? So what happens is that you have couple electrons. So the electrons, this pair of electrons essentially that forms the bond OH moves completely to oxygen because it's more electronegative. So now oxygen has these 2 black electrons, which are in a little bit bigger font, like that, right? So also, if you look at the, like now, the left side, right? So the oxygen here is neutrally charged, right? So, but now on the right side, see that electron essentially from H moved in the formation like together like with this lone pair together this with this pair of electron this electron moved completely to oxygen. So technically, so let's say this oxygen used to belong to this electron used to belong to oxygen. It's here, right? So now this electron used to belong to H, but now it arrived here. So technically you have an extra negative charge on the previously neutral oxygen, right? So neutral, you see here 1, 2, 3, 4, 5, right? But now you have 1, 2, 3, 4, 5, and 6. So you have 1 extra electron so that you added to the previously neutral oxygen. So consequently, you are going to have charge -0. -1, right? On the previously 0 charged oxygen. So same logic can be also observed when you break this HCl bond, HF bond, or OH bond in the carboxylic acid, and so on, right? So again, this is kind of like fundamental things that can be found in many various applications. So then hydrogen, if you look at the isolation at this hydrogen or H with a dot, it's going to be just considered as a hydrogen atom, which is bound to the oxygen, right? But now what happened is that, so this electron kind of like on the top here, so was lost by the hydrogen, right? So hydrogen used to be neutral. Now it lost a negative charge. Consequently, it has to become positive. So we'll have the H with a positive charge, aka proton, right? So that's going to be our proton formed here as a result of the acidic behavior of the alcohol. So that's it. That's our two compounds. So we must not forget the plus between them, right? So that's just the kind of product P, product Q, right? And that's it. And you say like P plus Q, right? So that's just a common knowledge. Like, don't forget that, right? So they just don't float in space. So that's gonna be our chemical reaction equation in this case. You have your reactants, you have your product, right? So you might have like 1 and 2, maybe 2 and 1, so whatever, right? So it depends on the chemical reaction, but don't forget the common things, right? So circle the charges is going to be good for you, maybe to like solidify that in memory further, right? And add sort of together what's it? In this case, two products of the chemical reaction of ionization, right? So that was ionization, or you can call it dissociation as well. You form ions in the course of ionization. Dissociation, because this bond is broken. It's kind of like this dissolution, right? So disassociation, but it's called dissociation. Dissociation. I think that's how you spell it, right? So dissociation, right? So this bond dissociated. So it's not associated, it's like opposite to being associated. All right. So anyway, so that's the alcohol. So now, since we have the segue, let's go on towards the classification of alcohols. So obviously, alcohols must have this like COH piece in that, right? In this like in the organic compounds in order to be called alcohols, right? So now let's take a look at the classification of alcohols. So I'm going to like erase everything. And yeah, so in terms of classifications, we have three classes, right? It's primary, secondary, tertiary alcohols. So how are they differentiated, right? So let's take a look at the skeletal structures, which will like prompt you to use this kind of skill a little bit more. So primary alcohols will be looking like that. So let's think about like 1-pentanol. And then the practice of drawing skeletal structures is in front of us. 1, 2, 3, 4, 5. So 1-pentanol, 1, 2, 3, 4, 5, 5 carbons, oxygen on carbon number 1. That's it, like 1-pentanol, right? So now we are going to have a look at, let's do, for example, 2-hexanol, because why not? That's our carbon skeleton, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, right? So 2-hexanol. So carbon number 2, lowest possible number, right? So to signify the carbon to which OH group is attached. So that's going to be number 2 as opposed to 1, 2, 3, 4, 5, right? So 5 is higher than 2. So 2 wins. So that alcohol, 2-hexanol. Finally, we'll have something more complicated, such as I'm going to draw it first, right? So then we will name it. 1, 2, 3, 4, 5, 6, 7. Let's do 7. So then we'll have another methyl here. And OH, right? So here we go. So that's going to be like, speaking of naming, right? So I'm not going to go through the nomenclature. It's going to be like way too much time, honestly. So yeah, please go over the nomenclature at your own time, but you can see some examples which you can kind of like put into the nomenclature fold, so to speak, right? So here we need to start naming, right? So to the carbon, which is to the end, which closest to the like OH group attachments. So this is far. This is closer, right? So like 1, 2, 3, 4, 5, 6, 7. So that's 7 carbons in the main chain, right? So this is not the main chain because it contains only 4 carbons, for example. So this is a methyl right here. So contains CH3. So now we have on carbon number 3, we'll have our OH, right? So the longest chain is 7 carbons. So consequently, we'll have the in the root. So we'll put this kind of like parent alkane root, right? So corresponding to the longest chain, so with the respective number of carbons. So it's going to be heptane, right? So from heptane, since we have the alcohol, we are going to obtain a heptanol, right? So carbon number 3 will contain the OH alcoholic group, right? So or hydroxy group attached to the carbon, which makes the alcoholic formation, right? So on carbon number 3, we'll have our OH that makes an alcohol, right? So that's how you can wrap your mind around this naming structure. So 3-heptanol, 3-heptanol, but something is missing, right? So what's missing? This guy. So it is a methyl, CH3. On carbon number 3, there is a methyl. So let's just say it this way, 3-methyl. 3-methyl, 3-heptanol will be obtained. So that's what we have here, right? So these are kind of names. So this one is 2-hexanol. This one is 1-pentanol. So that's like pretty straightforward, right? So this is a little bit more complicated. I just wrote it out. So now 3-methyl, 3-heptanol. So now let's take a look at the classification of alcohols, right? So they can be primary, secondary, tertiary. So these are your examples of those respective classes of alcohols. Like this. All right, so I'm going to use the colors, right? So here, let's colorize the in blue, the carbon that contains the hydroxy group, right? So that's going to be our like alcoholic formation, right? So if the organic compound has this like COH bond, so that is considered an alcohol. And specifically, so like we must make sure that this is an sp3 hybridized carbon, right? Because sometimes you can have the carbon with a double bond to the oxygen here, then you will have already a carboxylic acid, right? So because that's what carboxylic acids need to look like, right? So at some point we just need to like think about, okay, well, does it look like a carboxylic acid or does it more look like not a carboxylic acid, right? So there is no carbon, the blue carbon is not connected with a double bond to the oxygen. Consequently, it's not a carboxylic acid functional group, it's an alcoholic functional group. It is just sp3 hybridized carbon 2OH, right? So that's it. So now we'll signify that with the blue color. So then we're going to count the number of carbons directly attached with just like one bond away, being one bond away from the blue carbon, right? So they will be colorized in red. So here we go. You see, to the blue carbon, only one carbon is attached directly. Don't count those, they're too far, right? So directly means in our discourse, just one bond away, right? So they are just like one bond away. That's one bond away from the carbon with an alcoholic, with the hydroxy group, right? So, okay, great. So like here we are. So we only have one carbon, right? One red dot is going to be a primary alcohol consequently. That's it. That's your classification of the primary alcohols, right? So that's what it looks like in the classification pattern. So now you kind of like can get the gist perhaps. So then here we go. We need to count the carbons attached to the blue carbon, right? So one bond away, and there is another carbon one bond away here. Okay, so two carbons are attached to the blue carbon. Consequently, we have secondary alcohol. Now, moving on, we are going to identify already the blue carbon. And now let's count the carbons which immediately attach to this blue carbon or one bond away. One bond away, that's one bond. One bond away. And one bond away. So three carbons are one bond away, right? So from this blue carbon. So three carbons, tertiary. So 1, 2 secondary, 3 tertiary. So that's all you need to like know about classification at this point, right, of alcohols. So now let's move on to some more things such as chemical reactions, right? So we'll switch to like the kind of like beginning of the times, so to speak, or to the previous topics, which is going to be reaction of alkenes and alkynes, right? So that's what we're going to take a look at. Okay, so this will be now cleared. And then we're moving on to our, I guess, ultimate item at this point. So let's take a look at the reactions of alkenes, right? So we had hydrogenation, right? I'm just going to be speaking in terms, right? Because again, so it's not new, right? And I can just use them legitimately, right? So we had hydrogenation when we were adding the hydrogen molecule to our alkenes or alkynes, right? So we can also use halogenation when we would add the molecule of halogen to our like alkene or alkyne. So then we also had hydrohalogenation. So hydrogen and halogen are added to a specific alkene or alkyne molecule. And finally, we had hydration, right? So we also had the Markovnikov's rule for some specific kinds of alkenes, right? So that's like what we need to think about, like in broad strokes around the like reaction realm. So now let's take a look at some cases, right? Maybe we'll get some kind of like alkenes, such as, let's see. Sorry to switch the colors. So maybe alkene will look like that, right? So we are going to have some sort of, let's do some kind of cycle, right? So cyclo, alkane, and now it has this like a alkene bond to that, like this, right? So that's going to be our CH, CH2 piece, CH, CH2 piece right here. So if it undergoes hydrogenation, right? So it's going to be like H2 on PT. So PT is platinum, that's a catalyst. H2 is your reactant, right? So you're going to break the pi bond here. The sigma bond here will survive, and then you're going to make your saturated like alkane chain here. Basically, it will look like that. That's it. So you went from CH and CH2 to what? So now you have two hydrogens, right? So one hydrogen is added here, the other hydrogen is added there. So the bond is broken here, right? So you are going to have H2. So you have only CH, now you have CH2. Here you have CH2, now you have CH3 as a result, right, of the addition. So you add. So those hydrogens in the circles were added, right? So they were added. So the electron here, an electron there is liberated, right? After the breakage of the pi bond, which is made of like two electrons still. So each hydrogen also has an electron to contribute, right, to the bonding. And now you have carbon electron after breaking the pi bond. H electron, which is what they contributed when they came in as the reactant. Now you have the electron-electron covalent bond, electron-electron covalent bond. So that's it. That's your addition. You added, you didn't subtract, you didn't substitute anything, right? So you started with a particular number of carbons, hydrogens, you added two more H's, and now you have this original kind of like number of carbons and hydrogens in a new bonding pattern with two extra H's added. So that's your addition reaction, right? So then let's take a look at maybe, so for example, addition of halogen, right? So addition of halogen can be also done. So maybe some new alkene like this, right? So let's do the halogenation reaction. So typically, so this is done a little bit easier, right? So then hydrogenation. So we just add F2, no particular conditions for now. So then here again, so same principle. Some principles will remain, right? So the bond is broken, the pi bond is broken, and now we're going to have those kind of like liberated electrons available for bonding with the electrons of fluorine. So let's show fluorine here with its electrons like that, right? So broken, now they're free. Free. So the FF bond also has to be broken, right? So to liberate F with a dot and F with a dot. Dot stands for an electron. Connect. Now you have the bond, right? So make it connected to carbon. So now you have the sp3 hybridization, sp3, 4 single bonds, as opposed to single, double, right? So sp2. So lone pairs, that's your halogen lone pair pattern here. So yeah, that's it. So that's going to be your now fluorinated alkane, right? So there's an alkane still, but like with fluorides, right? But it came to be as a result of the addition of the atoms to the original alkene, right? So another one is going to be, let's take a look at hydrohalogenation. So, and then Markovnikov's rule at the same time. So those ones kind of like go hand in hand. I'm gonna do some elimination here of the drawings, right? So now let's take a look at some kind of like non-symmetric alkene. So like such as this one, right? So here we have carbon with 0 H's, carbon with 2 H's, so a different number of H's. So this is what will dictate where the, for example, like HBr will be added as a result of hydrohalogenation. So according to the Markovnikov's rule, so the hydrogen will go to the carbon, which has more hydrogens, right? So once this like pi bond is broken. So here we go. Sigma bond prevails. So maybe let's write things out a little bit here. Sorry, I erased everything. No, okay. Not so bad. Okay, so eraser, let's do that. So carbon, carbon. Methyl, methyl, don't forget them, right? So they just don't get lost as the reaction goes on. So that's something to keep in mind. So here you have 0 H's, 2 H's. Okay. So that's it, right? So now free electrons will be connected with H and Br. So that used to have like a bond. Now it's broken, right? So here we go. So H will go to the carbon with more H's. So this carbon has 0 H's. So this carbon has 2 H's. So consequently, we are going to attach H here. Make the bond, done, right? So that's your CH3. Just maybe like draw it in a little bit more like beautiful fashion. So now this carbon here, right? So no H's. So it will consequently will have Br, right? So that's what is left over. So Br is left over. 1, 2, 3, 4. 1, 2, 3, 4. 4 bonds. Okay, all set. That's your methyl here, right? So maybe just show them in the condensed fashion, because why not? It's good for our educational purposes. And here we have it, right? So sp2, sp2, sp3, sp3. So the new hybridization arrived, right? So that's something to notice. So you have new geometries of the carbons, and you have the product, right? So specifically, bromine was attached to this carbon, and then H was attached to this kind of like terminal carbon, right? Not the other way around. So the other way around would be like the wrong product, which was one of the exercises, right? By the way, to show the wrong product. So, but for now, just concentrate on the right product, and the wrong product will be kind of like whatever is the other combination possible, right? So that's it. You don't have like that many combinations possible here, by the way. So yeah, that's it. So that's going to be your product that you will form. That's going to be the so-called Markovnikov product, right? That satisfies the Markovnikov's rule. Markovnikov apostrophe S product, right? So, which in this case, it is, if you look at this, it is an alkane, right? It is a substituted alkane, right? So like by some other pathway, we could have started with an alkane, remove one of the H's, switch it to the bromine, then we would arrive at a substituted alkane. But this reaction is addition, because it's a different reaction, right? We started with an alkene and then we added HBr. So we literally say added HBr. So that's going to be the addition process. But it makes us the alkane, right, as a result. So that's just kind of some kind of like dichotomy to like think about, right? It's not an alkene with HBr. So alkene with HBr, that's the things that reacted. And then you make a new class of compound, right? So just be careful here. So yeah, that's pretty much it for now. So then maybe let's take a look at the alkyne reaction, right, as well. Just a little bit of the like extra review things. So alkynes have 2 pi bonds, which can be prone to those reactions as well, right? So we saw them. Honestly, there is like a slide that sort of like regurgitates all the reactions, right? And shows like in the listed table form the reaction types, right? So with like nice examples. So take a look at those slides from like your presentations, right? That's like a very fundamental. It's going to be good for your review. So, but here I'll just like in the interest of time show like one alkyne reaction, right? So with the excess of H2. So let's take a look at some alkyne, right? So maybe it's going to be like that. Triple bond, So that's it. That's your alkyne, right? So like 1, 2, 3, 4, 5, 6 carbons total, right? So this piece is going to be CH, right? So maybe let's write it out a little bit. So for our like intents and purposes of like figuring out the products of the reaction, right? So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6. Okay, good. So we are in good shape here. So notice how I don't bend this bond, right? I make it like straight in line with a single bond. So to signify the linear geometry of this carbon, it's an sp carbon linear geometry, just like from the beginning of this review session. All right, so now I'm going to add to that. Let's imagine we're going to add for each bond, if you like think about it. So you can add for each pi bond, you can add H and H and another H and H, right? So for each pi bond, you can add 2 H's, right? So theoretically, for an alkene, you can add, in terms of hydrogenation, you can add up to 4 H's, which is going to be conveyed by 2 H2 molecules. H2 molecule, 2 H2 molecules, 2H2, 2 by 2 multiply. If you multiply 2 by 2, right, then you will get a 4H's total will be added. So 4H's total can be added. So electron, electron, CH bond, CH bond will be formed. CH bond, CH bond will be formed. So let's do that, right? So we are going to do that. We use platinum as a catalyst. Mind your conditions where they're supposed to be shown, right? So it is just kind of like peculiar to those reactions, and we need to remember them at this point, right? So some reactions just go like alkene plus HCl. You figure out your product with Markovnikov rule, if it is applicable, right? So in other things, you need to remember the conditions. So these pieces, CH3, CH2, 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 are staying intact, right? So we literally just redraw them, CH3, CH2, CH2, CH2. So then we are going to add carbons. So this is sigma bond that kind of stays, right? Actually, you can probably envision that we are going to obtain alkane here, right? So you can continue drawing in this kind of like tetrahedron resembling fashion, right? So that's your terminal carbons, C and C, right? So C and C. So now they used to be like that. So this terminal carbon, so the most terminal one, or this one is a penultimate carbon. So this had no H's, this had just one H. So let's just show it as such, right? Sigma bond stays. That's a sigma bond here. So those bonds are broken. And now they will be, okay, having those liberated, they will produce the liberated electrons, right? So that used to be the bond, and this used to be the bond, if you think about it. So now let's just show the electrons which are available for bonding, right? So then we're going to surround it with hydrogen atoms. That's your 4 hydrogen atoms, with the dots signifying their electrons, which are available for the making of the bonds. Excuse me. Bond, 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 and bond. So this one is a little bit ugly. So let's redraw that, and it's going to be something like that. So this is that, bond, H. So I just want to make it more like a tetrahedral shape. Tetrahedral, tetrahedral. Now you have your alkane, right? It's nothing more than 1, 2, 3, 4, 5, 6. Okay. That's it. So 1, 2, 3, 4, 5, 6. So now you made nothing more than hexane and alkane, right? You went from alkyne to alkane. So yeah, those are like things to keep in mind. So, but yeah, by no means I cannot like fit everything, like all the possible information here from the lectures, because we had hours of lectures, right? This is just 1 hour of review. So it's more like serves you to like ask yourself questions, right? What am I missing, right? So what's not unclear, and then review that, or like maybe like see me before those exams and such. So yeah, that's like what we have for now. I think it's good at this point. So maybe about the OH bond, right? So like people were mentioning charges a lot, right? So like in the first exam. So I just wanted to make something clear, right? So when you make a bond, right? So like covalent bond, there are not yet charges. If you look at the ionic bonds, right, such as like sodium Cl, right? So then those ones will be made of ions, right? An ACl bond will be made of like sodium plus ion and Cl minus ion. So the ions will have charges, right? So the bonds before they break, so they have like partial charges, right? If any. So that's just true about, for example, in the bonds in alcohols, right? Such as CH3, CH2, OH. So CH-CC bonds are non-polar, right? So they will not have like partial charges. Maybe CH bond will have a slight partial charges, right? Because carbon is still technically a little bit more electronegative than H, but their electronegativities are very close. And then CH bonds, because of that, are considered non-polar, right? So, but C and H will have the partial charges. So O and H, this is a polar bond, so which will have more prominent partial charges. So since one of the atoms, oxygen, is more electronegative, that will be kind of like drawing this like electron pair, right? So towards itself. Let's show it with this kind of like hollow arrow, right? So it's an ugly arrow, but that's just where it goes, right? So this lone pair will be like drawn towards oxygen, which will make the by default neutral oxygen partially negative, right? Because it has extra, essentially, this electron is getting closer, right? So it gets like the whatever, like 1, 2, 3, 4, 5, 6. It gets like the 7th electron in addition, right? So 6 electrons around the oxygen, it's like neutral atom, right? So this extra electron, number 7, right? So that's getting towards kind of those outer shell electrons. Then it will make it partially negative, right? It's not like plus, like 0 and -1 charge becomes -1. It's like more like a 0 and maybe minus like slight charge from this negatively charged electron, maybe like minus like 0.7, for example, right? So that's what will make it like partially negative, right? Delta minus. So not like -1 straight up, but delta minus, partial negative charge. So then, consequently, this guy, the hydrogen, partially loses its electron, right? It used to be neutral, but now it loses a little bit of the negative charge from the previous neutral charge, right? Consequently, it will become a little bit positive, right? Or partially positive or delta plus. So that's what it will have for the OH bonds. And now you can kind of try to discern this OH bond in many other compounds. Well, not so many, actually. It's like water, alcohol at this point, and carboxylic acid, right? So that's where we see the OH bonds. And then kind of like ask yourself, who is partially negative, who is partially positive, and why, right? So yeah, and then like how does that happen? So that we kind of like looked at this right now. So yeah, at this point, this is done. So it was a little bit of the medley of information, but that's just how it is for now. So, and like further things are up to you to like review as well and like ask questions to yourself and see me if possible, if necessary, right? So, and then of course, there should be a little bit more time before each exam that will accommodate all those like questions and discussions and such. So, but it is just kind of like the time management thing at this point. And a reminder to those who want it, right? So, want to have this time management. It's kind of an important skill in your life in general. So, yeah, and we all can kind of like benefit from that. All right. So anyways, so have a good day and bye everyone.